Okay. Okay, well, nice to meet you again. I'm Kaymie. Today I'd like to talk to you about my thesis work on quantifying human balance control and performance to inform therapy. Yes. Okay. So before I jump into my talk, I wanted to briefly introduce myself. So I'm originally from Tokyo. I grew up there until I was 18, and then I came to MIT for college. And I've studied and been studying mechanical engineering. What really drew me into engineering was that I felt very empowered to turn an idea into kind of a real project or product. And then also I got very into robotics in my undergrad and how it's very interdisciplinary. But then also in the back of my mind, I had a keen interest on medicine, human balance, and things like that. So I was very happy to work with Professor Neville Hogan at the Newman Laboratory for Biomechanics and Human Rehabilitation, trying to work on technologies to assist people with mobility impairments. And to be determined, I'm planning on graduating in the winter, or hoping to graduate in the winter, so I'm looking for opportunities for afterwards.
A shout out to Wally in one of those robots.
Oh.
Can I see that?
Yes, this was like actually my first robot that we built, and it was a very stupid robot, but it did really well in this competition because it just explored the room very randomly and bumped into walls. So there was like these switches, and so we called it wall B for wall bounce. But yeah, this one was my sophomore, I think, project, and it's a robotics competition class, and it was supposed to lift this kind of really heavy thing up and get a lot of points. So it was like a racket pinion system, and I don't know, it's getting darker, but this one is actually an arm that's supposed to theoretically help with paraplegic people who can only use like one arm, for example. And then, so for example, if you're pulling a drawer, if you only pull from one side, it gets like locked. So we tried to like synchronize the movement with the person. Yeah. Okay. So
that after my shoulder surgery.
That's over.
Yeah, so the talk is kind of outlined as so motivate my talk, I'll talk about the balance control side of things and then the balance performance side of things, and then conclude the talk. So I'm sure you all know this, but balance is a very important aspect of our mobility. So to live our daily lives and maintain our overall health. But neurological disease and aging can disrupt our ability to balance and increase the risk of falls. So timely and accurate assessments are really important to prevent these falls from happening. So thinking about balance assessments, I found this previous study that asked physical therapists on what they think about assessments. And it seems like they think that quantifying impairments and balance outcomes are very important for patient care, but they feel quite split on whether the existing standardized balance assessments really meet their needs. So I think one reason for that could be that current standardized balance assessments can have sensitivity issues and ceiling and floor effects. And so a lot of therapists end up just using non-standardized movement observations, such as just watching people walk around to kind of diagnose them or assess them. And I've actually been doing like PT for my back. I'm getting old, so and I've experienced that I've experienced that firsthand, where everything is not very quantitative; it's very like subjective. But yeah, so there's clearly a gap between the therapists wanting quantified assessments, but there's not quite meeting their needs. And then on top of that, there is the aging population. In Japan, where I'm from, and also in the US. For example, in the US, those over 65 is expected to outnumber those under 18 in just 10 years. So this imbalance in the population can cause a shortage of caregivers and strain our healthcare system. So I think that automated assessments in which therapists or caregivers don't have to provide extensive support to conduct assessment could help alleviate the strain. So the goal of my work is to develop assessment methods to understand and detect balance impairments. So I've been working on two projects. So the first investigates the underlying neural control strategies of balance. And then for this project, I'm using a novel experimental technique that I'll talk about, and then conducting system identification through modeling. And then the second project concerns an instrumented cane that we developed that can continuously monitor and quantify balance performance. And I've done human subject experiments, and we've shown that we can predict well-established signals. So although both of these projects concern quantification of balance, the first one is focused more on control, the balance control side of things, and then the second one is more on performance or ability. So focusing on the first project. So the main goal of this work was to clarify and quantify the underlying control strategies of quiet balance, because it's not quite fully uncovered. So I'll talk about three projects that I've been working on. So the first project looks at healthy younger balance, and that helped us establish the method. And we looked up healthy younger but challenge balance to verify this method. And then finally, we compared older and younger balance to apply the method and quantify the effect of aging. And ultimately, I think quantifying and understanding the underlying mechanisms of balance can lead to improved and tailored therapy. So first, before jumping into the studies, I wanted to highlight that all my work is on quiet balance. And so there's no perturbations being added to the system. We're just looking at the person standing. And while there are many seminal works on perturbation-based studies, it's also important to understand how people naturally stand, because humans can be very adapted to perturbations. So a lot of the studies on quiet balance have looked at this foot ground force, using a force plate. So they measure the point of application of this force, or otherwise known as the center of pressure. But I think there's other information that we can extract from this foot force. So for example, the angle of this foot force, denoted as theta F here. Previous researchers have looked at the combination of this placement and orientation of this foot force. And so if you imagine a person standing, their involuntary swaying, and then so their forces are kind of shifting like that, F1, F2, F3. And when you draw the lines of actions of these forces, they intersect roughly at a point in a plane. And they call this the intersection point. And we're interested in how this height of this intersection point varies, and we call that ZIP. Okay. So the intersection point is useful because its height relative to the center of mass can dictate how the body moves. So let's say we're assuming that a human can be modeled as a double inverted pendulum with ankle and hip joints. So when this intersection point is above the center of mass, then you have kind of a rigid body motion, so it's moving together. And when it's below the center of mass, you have the out of phase motion, kind of like this. And for example, if the intersection point is at the ankle, you're controlling the balance solely through the action of the hip. And when these previous researchers looked at this intersection point height in the frequency domain, they noticed this consistent pattern across healthy young subjects in the sagittal plane. And this, yes. Mm-hmm.
I'm wondering, so like as a physical therapist, we talk about like the movement strategies.
Yes, yes.
So like a hip or an ankle strategy.
Yes, it's very similar.
So it's kind of finding that if the IP is above the center of mass, they're using more of a hip strategy.
Or it's the opposite, yes, the ankle strategy.
And then below is so you're saying above is the ankle strategy?
Yes, where this kind of moving together. and then moving out of phase. And so that's mostly, I'll go into this, but that's mostly due to like the biomechanics, less control. But I'll show you how some of it is also dictated by control. Yeah, so they saw this consistent pattern, and in the lower frequency, they found this IP above the center of mass, and in the higher frequency, they saw below the center of mass. So when they saw this consistent pattern, they suggested in their paper, oh, this could be, this could be showing us a signature of neural control. I think biomechanics also plays a role. And so our first study aimed to clarify the extent to which this frequency dependence of the intersection point can be attributed to biomechanics or neural control. So in other words, in simple terms, given a variety of control parameters sets and an assumed biomechanical model, would it always yield the results that we saw in humans, or would it kind of change with the pattern shift based on which control parameter sets we're interested in? So we did this by first developing a model. So we have this plant, which is the double inverted pendulum with ankle and hip joints. And then we stabilize this double inverted pendulum using an optimal controller. So this optimal controller is called the linear quadratic regulator, LQR. And two important things about LQR is that number one, it guarantees stability. And we're stable, we're not falling over everywhere, so that's important. And then number two is that we wanted to test this assumption that humans minimize their control effort. And by doing that in this LQR framework, we were able to reduce the parameter space to just two. So these were beta and sigma r. So beta basically dictates the relative penalty that we have on using ankle or hip torque. And so when beta is greater than 1, we have more ankle penalty than hip torque penalty, and vice versa. And then we also added white noise to the system, to the torques. And so sigma r dictated the ratio between the two joint noise sources. Okay, so we explored different control parameters, and we found that varying the control parameter beta affected the intersection point's frequency-dependent pattern. So this suggested that there's kind of a control parameter set that best fits the human data. And results showed that a controller that minimizes overall joint control effort while emphasizing the use of the ankle torque led to a close fit of the human data. So this is the intersection point height again, normalized by the center of mass height, and then frequency. And then the X's are human data, and then the circles are simulation. And so this showed that this paper showed that a simple dynamic model and controller could be used to understand the underlying mechanisms of balance and impairment. Oh, yes.
Is that data for a group of people or for?
Yes, for a group. I didn't put the error bars, but in the many slides before, there was this one. There's more error bars, yeah. So there's this, I think, like 12 subjects, maybe.
So sometimes when you have curves like that and you look at one person, then it doesn't necessarily.
Yeah.
Like that, is that true?
No, I think overall it looks pretty consistent. Like, and so the error bars are not too big. So it's not like, one person's going like this and one person's going like this. It's more like there's just subtle differences between like where it crosses this center of mass or.
Was there anybody who really deviated? Like if you look at an individual subject?
For this data, I'm not sure because it's from that previous study, but maybe later on I'm going to compare the older and younger people. And I think that in my back of slides, I have the individual. I might, so I can show you that. But yeah, overall, it doesn't shift too much. Yeah, from like this general pattern. And I'll talk about that too.
And what was your controller outputting? That was that torque or
Yes.
angle or
Yes.
torque? Okay, and then you were measuring these emergent properties of like where the center of pressure ended up, or where the
Where
IP ended.
yes, exactly.
Okay.
And so your model then
Well, based on the outputs of the model, so we have a state space model, and we can compute the horizontal and vertical force as well as the center of pressure. And so we can compute the ZIP from that.
So are you?
I didn't get
doing-
into the details of
Yeah,
that.
so sorry, are you assuming, do you have a foot? I mean, are you assuming?
Yeah,
like,
we're
that there's
assuming a
length of the
stationary.
foot And then like you use a
No,
fork?
it's like a stationary foot, so there's just a point there.
But it's not a degree of freedom.
For, what do you mean?
Like, can the foot come off the ground?
No, no,
Okay.
yeah.
And so, do you ever have, well, I guess if you're doing LQR, you'll probably minimize it, but do you check to see that the center of pressure doesn't go beyond what the foot length?
I guess, no, I haven't checked that specifically, but I think, yeah, I guess this is, we're not minimizing the center of pressure trajectory. Actually, we're looking into that maybe for like stroke patients, but that's a whole nother thing. But yeah, we're minimizing the control effort. And so, yeah, we're not necessarily like limiting the center of pressure, range of motion, or, yeah. Okay. Just. Okay, so on to our next study on, we're looking at healthy young balance still, but challenge balance. So we tasked participants to stand on a narrow beam for 30 seconds. So we looked at on the beam and on the ground as a baseline. And in this study, we actually looked at the frontal plane behavior of the CIP, in addition to the sagittal plane for the first time. So I was again able to achieve good fit of the human data across all of these conditions. So these graphs are again showing the intersection point height normalized by the center of mass height, and then frequency in the x-axis. The first row is the sagittal plane data, the second row is frontal plane data, first column is ground, second column is beam. And as you can see, the general shape of the curves have been consistent for all of these, even from the previous study, where the intersection point height is above the center of mass at low frequencies and below the center of mass at high frequencies. And then notably, the minimal control effort again achieved best fit for all of these conditions. So I wanted to specifically compare two conditions, both in the frontal plane, on the ground, and on the beam. And you can see that again, the pattern is similar, but if you look at the details, such as where this curve crosses the center of mass height or the high frequency asymptote, then it kind of it varies. And that's reflected in the simulation results, the best fit control parameters. So on the ground, it was suggested that there was more ankle use, and on the beam, there was more hip use. And I think that makes intuitive sense because on the beam, your center of pressure range of motion is limited. And so I think subjects probably had to result in a more hip dominant strategy. And so this general paradigm was able to quantify the control using the intersection point, even for challenging balance conditions. And so I think that showed promise for work on older and impaired populations. Which brings me to the third topic. So this compared older and younger balance. We used a public data set, 60 seconds of quiet standing data in the sagittal plane, again on a force plate with feet side by side. And we had 65 younger participant data, less than 6 years old, and then 38 older participant data. So first, looking at just the human data, we compared these two curves, and we found that there's statistically, the older and the younger participant curves are statistically different at all frequency levels, and where the older participants had a higher intersection point height. And we searched through the best fit controllers, and we were able to again achieve relatively good fit, where the X is the human data, and then the colored circles are the simulated data. Okay, so we also quantified this time we quantified the best fit control parameters for each participant and found that beta was statistically smaller than in the younger adults case, for the older adults than in the younger adults case. So to remind you, when beta is less than 1, we have more hip torque penalty, so more penalty on using the hip. And so so the older participants had even more penalty than the younger participants on using the hip. So in other words, there was more use of the ankle joint in older participants, and some previous studies have shown that increased ankle stiffness counteracted destabilizing forces in systems with neural delay. And so because older adults have been shown to have more neural delay than younger adults, we might be able to say that older participants may have compensated by using their ankle more. So we also analyzed the closed loop stiffness closely to understand the role of yes.
Just, I think this is the case, but the older and younger adult data, that was just on the floor, not on a beam, right?
Oh, yes, sorry, this is very
Then-
confusing.
That's okay. And then with the older adults, like, was there any data on what their fall risk or history is?
Oh, yes, I'm not sure if there was fall risk, but they had data on different balance tests, like mini BAS.
Right, yeah.
Things like that. So I can show you actually graphs on that later if you're interested, yeah.
Well, I mean, it's
We
like.
do many
the-
best on everybody.
That's what I'm saying. we have
Yeah,
many
yeah, yeah.
best
I
and-
think this data set was relatively extensive, so yeah, we could compare these measures against these other.
You know, and some of the balance training I've seen that like teach people how to use it.
Yeah, so I can say, like, the balance beam stuff, like, when you work with patients that have difficulties, who are often use a balance beam to try to help facilitate a strategy.
But like, if it's not good for a system with a delay,
Right.
is it the right thing to do?
Yeah, it's true.
Yeah, but
We can measure it.
yeah.
No, we're
Very
seeing a lot of delayed, like, brain activity in older adults.
But then if it's delayed, can you train it? So that-
To be determined.
Yeah, it's true. Yeah, this is,
We had a talk on this yesterday. The recording failed.
oh no.
Yeah.
So this is, for example, comparing that same beta parameter with the mini best score. And so you can see that overall, lower beta parameter, which was the older subject's case, is related to a lower mini best score.
Yeah, like that.
But
Adult populations.
how young is younger?
Everything, we had a cutoff at 60. So,
Okay, so not,
Not our cutoff, yeah.
yeah, so
not like, if we run it on our healthy adults, there's not gonna be a spread like that.
We get a ceiling effect with.
I think this is the age spread. So most people were under 40, but there were a few, yeah. And so you can see here that, well, this is more of a discussion point, but you can see here that there's some younger people who are more in the older people region of the beta parameter, which is
Because
interesting.
you have like a gap, you have a lot of people between.
Yes,
20,
yeah,
40,
yeah. So that's a little bit of
60.
weakness. But
That's interesting.
yeah, so I think, yeah, this is kind of interesting. It could suggest that maybe these people have some other things going on. I don't know.
I mean, we see a spread.
Yeah.
And big spread.
Okay, so we also analyzed the closed loop stiffness closely to understand if the extent that neural feedback may have been used during balance. So this is, again, the optimal controller spits out an optimal gain. So this is called KLQR, or I'm calling it KLQR, and it has stiffness and damping components. And that stiffness component K can be further decomposed into symmetric and anti-symmetric components.
When you do
So,
your controller, like, are you putting noise in the simulation, or you're not using it in your problem, your optimal control problem?
No, yeah, it's more
So you're
like
just solving for a
after,
non-noise, like.
yeah, so there's other things like LQG or something, which incorporates noise, but I think it's different. So we're
Yeah.
just adding, additive noise to the, torque, control torque.
So you're taking optimal controls gains from an
Yes.
idealized system.
And then getting the
Run
power
it
control.
through the simulation where you put noise into the, like a perturbation.
Yes, kind of.
Okay, do you know how big you can make that noise?
In terms of.
Like, did you vary the amplitude of noise?
Yes, and I don't think that like absolute amplitude plays such a big role. So that's why we were mostly playing with the ratio of the amplitude,
Okay,
between the ankle and the, yeah. Okay, so we can decompose them into symmetric and antisymmetric components, where the symmetric component represents forces that may arise from either intrinsic muscle behavior and or symmetric intersegmental feedback, whereas the antisymmetric component represents forces that can only be due to asymmetric intersegmental feedback. So when we look at the ratio between these two components, so K ratio, then we can quantify how much asymmetric intersegmental feedback is going on. So when we compared again, we did this for every participant and plotted it like so. And we see that first of all, both older and younger groups exhibited this use of neural feedback. So this agrees with previous studies that have said that intrinsic ankle stiffness alone is not sufficient to maintain balance. And then also older participants had significantly larger antisymmetric components, or K ratio. And so that suggests that there was more use of neural feedback to potentially compensate for some effect of aging. And one potential reason for that could be diminished intrinsic muscle stiffness, or things like sarcopenia, weakened muscles. Okay, so in this part of the talk, I showed how I've developed an assessment method that can quantify the control strategies that underlie balance via using this intersection point analysis and conducting system ID using an optimal control method. So we looked at healthy younger balance to first establish the method. Then we looked at healthy younger but challenge balance to verify the method. And then finally, healthy older and younger balance. We compared those two to quantify the effect of aging. And I think this work is impactful because just by stepping on a force plate for less than 1 minute, a patient could have their shift from whatever average is measured without a much extensive support from a clinician. And not only that, but this method can also quantify this control strategy that underlies their balance or their balance impairment. And I think that could be informative for therapy methods. And so in the future, or like currently, I'm looking at post-stroke balance and seeing if we can similarly quantify control strategies.
so what data do you need to do that? You have the center of pressure, and then do you have,
The
do
force,
you get the center of mass, or do you just need their height?
yeah, basically, we can, since we're doing 5 balance, the center of mass height doesn't change so much. And so we just use like a ratio of their height.
Okay, and you don't need like kinematics or?
No, yeah.
Okay.
Yeah, and I guess if you really wanted to accurately measure the center of mass, like I think the other researchers that we've been working with have been looking at this ZIP in relation to the position of the center of mass, like the horizontal position of the center of mass, and you can also estimate that using the horizontal force, so the shear force on the force plate. Yeah. So either way, just the force plate.
So you could take your simulation and just give a perturbation.
Yes, but I think the thing is that the spectral method that we're using to kind of quantify this this intersection point assumes like a linear time invariant system. So that's why this works for quiet balance, but I'm not sure how it would work if we
have pretty good luck with doing
Okay.
stuff like that, where you
Okay.
just try and stabilize it with the linearization method, and then
Okay.
you run a perturbation,
Mhm.
and it actually works remarkably well.
Okay.
So Nate Gunderson did it on the hind limb, and then, Jeff Bingham's stuff also needed like a stability margin, stability radius, because we had a delay. We just used a linearized system, and then he just simulated the perturbations that we had.
Okay.
And, yes, it worked remarkably well. And the paper with Tom Van Well and Friedel de Groot, similarly, they had, we did stochastic optimal controller,
Okay, okay,
but it was just with noise, and then he also imposed perturbations,
okay.
and we were
Yeah.
getting pretty good results.
With that one, was it sensor noise?
For sensor and motor noise. Yeah, so because we did the standing balance one, and then got the like Paterka results with the, sort of different sensor gains. But then he also just went ahead and did translations and rotations, because that's what we do here. And you know, you can get out pretty good results.
Okay,
Yeah, it's amazing, like the linearization for
Yeah,
those small
yeah.
perturbations actually works pretty well.
okay, yeah, maybe. I'll have to think, yeah. Yeah, okay, yeah, I'll have to think a little bit more. We're actually, yeah, finding this, instead of like, we used to be, simulating all the data and, but since that process is quite slow, one of my colleagues, she developed a way to like analytically find this, intersection point curve, and then that's how we do like all the parameter search, because it's very fast.
Yeah, that's.
And so I think that analytical method might rely on this like stationary noise as an input, but
No,
Yeah.
all of those things I talked to you about have stationary,
okay,
everything's stationary.
yeah, okay, okay, yeah. I mean, yeah, we just might have to try it.
Yeah.
Okay. So moving on to this next section, I'll talk about my work on an instrumented cane that can continuously monitor balance performance. So returning back to what I initially mentioned about the dangers of falling, assessing balance is very important because falls can be detrimental and even fatal. And so timely and accurate assessments are crucial to prevent these falls. But how can we identify this elevated risk of falling? So unfortunately, some commonly used clinical balance assessments like the 4-stage balance test or the time it up and go have been shown to be not a significant predictor of falls. But on the other hand, things like sway velocity, which can be measured using a force plate, have shown relatively high accuracy in predicting whether a patient would fall in the next year. But there are some obstacles to using a force plate. For example, it can only be used in a clinic, and visits can be rare, 1 to 2 times per year. And so I think continuous evaluation would be able to provide stronger data. So in thinking of a continuous method to measure balance performance, canes came to mind. So canes are already prescribed to reduce fall risk, and so many people are already accustomed to using a cane. And so we thought that we can modify an existing walking cane to predict sway velocity. So we instrumented this cane with motion and force sensors, and we developed a linear regression algorithm that makes predictions on the sway velocity. And so this cane would travel with its user and could provide continuous evaluation of fall risk. And this means we could examine trends over months or even years. And also I wanted to mention that this work was mostly done by an undergraduate student who was working with me. Okay, so I'll walk through the development of the predictive model. So first we'll talk about data collection. So we collected data from 8 participants, all healthy and young, and we ran 40 trials per participant, in which they stood on this unstable balance board, which was on top of a force plate that measured their true sway velocity. And they're using this cane in the meantime. And there's 4 conditions of varying stability so that we can measure a range of sway velocities. And so we had 2 stance conditions, and then eyes open, eyes closed. Then we applied a test train split, and then we windowed or divided the data into small chunks. Then we computed the features. So again, the sensors we had was an IMU and a load cell, so we can measure acceleration, velocity, angle, and force. And then we ran that through different features, so like statistical methods, so like mean, maximum, standard deviation, and many, many more. And then we can come up with a feature vector, which consists of things like mean acceleration in the x direction, maximum force, standard deviation of force. And then we selected features that are that correlated most with sway velocity, while removing features that are redundant with the other selected features. And then we trained the model using a linear regression algorithm to fit a group of feature vectors to the true mean sway velocity. And then the weights were trained for each individual participant. So then we tested the model and then computed the success of this model. So we did that by comparing the predicted sway velocity with the true sway velocity, and we computed the sway velocity in both the medial-lateral and the anterior-posterior directions, and then also the magnitude in 2 dimensions. And then we computed the R squared. So this is one kind of representative result. So this is a graph from one of the models, but we have on the y-axis, we have predicted sway velocity magnitude. On the x-axis, we have true sway velocity magnitude. And if this were a perfect predictor, the test points would follow the red dotted line exactly. And so in general, that pattern is, or that trend is followed, and we had a relatively high predictability with an R squared of 0.73. And then we wanted to further understand the data and see which features were actually important to predict sway velocity. So we computed a Pearson's correlation between each feature and the mean sway velocity. And we found that the cane angular velocity components correlated strongly with sway velocity for every single participant. And then, but surprisingly, the force applied to the cane did not correlate strongly with sway velocity. And we think that this is because we ran this first study on younger people, and they didn't necessarily need the cane for weight-bearing purposes.
Why is that angle,
Yes.
why is the average correlation with sway 0.8, but your linear model was like 0.7? Shouldn't you have more features and do better?
Not necessarily. This is also using all of the data to look at this correlation, because for the model, we're doing a test train split. And so there's, you're only taking some of the data to train the data, and then we're computing that R squared for just the small test data set. So yeah.
That just means that there's some people who have different relationships to this way.
Yeah, I think so. And yeah, I mean, yeah, and we were, well, and then also it's like I guess the average is, the standard deviation is relatively small here.
So I can, in that graph with the, sorry about my, with the velocity magnitude that was truest or predicted, that has nothing to do with the cane.
So the predicted magnitude, the predicted sway velocity is purely coming from the cane's outputs, and then the features that were computed.
That's not right. So you're predicting their sway based on the cane's movement.
Yes, exactly,
That-
exactly. Yes.
And then use a course plate.
Yeah, yeah,
Yes, exactly.
And sorry, were you doing this with time series data?
No, we computed different, like mean or maximum.
Oh,
like,
and you do that for sway velocity as well.
Oh, no, for sway velocity, yeah, we have time series data of the mean sway velocity for that, for example, window of data.
Oh,
Yes.
right, that's the windowing.
Yes.
Okay.
Yeah, I kind of
But
give
so
you
you're
a
taking,
lot.
I mean, over a period of time rather than like doing a time point by time point correlation of like what this way.
Yeah, but we have
velocity-
some overlap in the windows that we're doing. But
Yeah,
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 it's
but
not,
you're,
it's not
at the
it's not a
resolution.
moving, yeah, it's not a moving.
When you held out data for testing, did you hold out entire trials or just windows within a trial?
We divided the data into like three, so with the trials.
Okay.
And then, we ran it through like many iterations of like dividing the data into test and train splits.
And did you hold out entire subjects or did you hold out?
No, yeah, we like randomized everything, but just the trials,
Then which factors from the cane are included in that particular file?
So mostly things to do with the angular velocity, I think.
So I'm trying to,
So-
you need everything from the cane measures. Sure.
Yeah, we like, as, at least for the younger data, it might change if we have like actual cane users. But we didn't, if I remember correctly, we didn't have, many features that came from the force itself. Yeah,
The velocity of the cane.
yes, yes.
Well, it's good because the force sensors are most expensive.
No, no.
Right, but with people that actually use a cane, they're more likely to have force through the cane. Is that right?
Yeah, and then, I mean, this force is like just a axial, like load cell.
Oh, yeah, the
so
load
it's
cells are not
It's very cheap
expensive.
either way. So this cane is like relatively cheap if you were to try to make it.
Toughest part would be getting somebody to use a cane with that stuff on the outside.
Yes, so, yeah, we try to make it as like,
Put it on the
You
inside.
could make it, build it on the inside, yeah. they're
yeah, I
all-
think.
I mean, the
it could
actual
be-
sensor is like this big, right?
Yeah,
It's
yeah, I
not-
think it
they're
could
all-
be,
all- Those canes, all much better, but there's no.
Everything's finished.
yeah, yeah, if you have like, nice like designers working on it, then
I
I'm
mean,
sure.
it's in my phone.
Yeah, yeah, and then the load cell is already kind of embedded
It's in my
into
phone.
embedded into the foot of the cane, so. Yeah, we try to make it as like, as seamless as engineering students can do.
Which is not seen.
Yeah.
Sorry.
No, yeah, I mean, we have like a huge Arduino on it, so
Yeah.
that will probably change if you have like,
Prototype.
yeah. yeah, so yeah, we have, yeah, it looks like that, basically. But yeah, so we did this with younger participants and, so this is the first, at least to my knowledge, the first intermittent cane that can predict quiet standing ability. So there's a lot of canes that can do walking and like distinguish between people sitting and standing and things like that. And then this can be a continuous portable alternative to assess balance. And I think that if we are able to do frequent assessments outside of the clinic, in the clinical setting, then we can, detect the risk of falls earlier, or just to
Yeah,
detect
you have
balance.
some alarm, once you exceed some threshold.
Yes, exactly. And you just have more
you
data
can
on that
electric shock
person. That might make them fall too, but yeah, we've been, testing
Reset.
on older adults as well. And, I think they like how, we're working on technologies that, can potentially help them. So, that's been a very positive experience, and we're trying to assess if this cane can actually work on, this target population as well. Okay, so today I showed you my work on quantifying balance control and then also performance. And while both of these projects contribute to quantifying balance assessments, the cane is particularly powerful because of its portable nature, how you can continuously evaluate balanceability. But on the other hand, this first project with the intersection point analysis can quantify the control strategies that underlie balance control. So they have both strengths.
Could you
Mhm.
take the balance control
Mhm.
and, it's to me like you wanna do this not just with cane users, but could you do this with some sensor you put in people's shoes to then? give that
Yeah,
info?
I haven't seen, I think, like Connor Walsh's lab at Harvard, they're like developing those sensors that can measure not only like center of pressure, but also the shear force component, but I'm not sure if they can measure it quite to the degree that, for example, quiet balance is very small,
Right.
the horizontal force, so I'm not sure yet, yeah. but that is one thing I have thought of too.
Cause you could, I mean, could you, like, would it help at all to have like use both accelerometer and pressure data?
Maybe, yeah, that's true. The thing with accelerometer is that one of my lab mates looked at like quantifying balance through just IMUs or
Right.
even motion capture, and again, quiet balance is so like still
not
that
much
the
more.
heartbeat kind of like overpowers your sway. So it's a little bit of a challenge, at least with the current state of technology. Yeah. Yeah, so, I guess like looking forward, I plan on continuing to work on these projects through looking at the stroke data for intersection point analysis, and then the older adults data for the cane. And then in the long run, I hope to, while continuing to look at balance assessments and improving balance assessments, I also want to investigate how we can address, like learn from these assessments and address actual mobility impairments. So that's my long-term goal. Yeah, and then, so thank you very much for listening. These are some of my collaborators, as well as my lab mates, and my funding sources that made this possible.
Other questions? We did a lot during, so.
Yeah, thanks for all the questions.
Yes,
Yeah.
always. What time is it?
Oh,
9:53.
Okay, so